You know, we're swimming in invisible forces every single day. Sound, light, they're all waves. But what if I told you they don't always travel in a perfectly straight line? It's true. They can actually bend. And today, we're going to dive into exactly how and why that happens. I mean, think about it for a second. You've definitely experienced this. You're walking down a hallway, you can hear a whole conversation happening in a room up ahead, way before you can actually see who's talking. So, how is that possible? How can sound get around that corner when light can't? That little everyday mystery is exactly what we're going to solve. So, what's the secret? Is it some crazy complex physics? Not at all. It's a basic property that pretty much all waves share. And believe it or not, it all comes down to just one word, and that word is diffraction. Okay, I know it sounds super technical, right? But all it really means is the bending and spreading of waves when they hit an obstacle or go through an opening. So that conversation you hear around the corner, yep, you're experiencing diffraction in real time. Pretty cool. Okay, so to really get a grip on this, let's look at a couple of scenarios. We're going to start with what I like to call the gap challenge. We're going to find out what happens when a wave tries to squeeze through an opening, like, say, a doorway. Now, what happens here isn't just random, it's totally predictable, and it all boils down to the relationship between two really simple things. The size of the wave itself, we call that its wavelength, and you guessed it, the size of the opening it's trying to get through. And this relationship, the one between the wavelength and the gap size, well, that's the absolute key to the whole thing. It is the secret recipe that tells us exactly how much a wave is going to bend. And this lays it out perfectly. Just look. Over on the left, when the wavelength is about the same size as the gap, bam, you get maximum diffraction. The wave spreads out in these big, beautiful curves. But now look at the right. When the wavelength is much, much smaller than the gap, the wave just kind of sails right through with almost no bending at all. So here it is. This is the big rule of thumb you need to remember. For the most dramatic bend, the wave size needs to match the opening size. Got it? Because that one little rule is the key to understanding everything else. Okay, that was the gap challenge. Simple enough. But what happens when there isn't a gap? What if a wave just runs into a single edge, like the corner of a big building? Well, here's the best part. You already know the answer. Seriously, the exact same principle is at work here. It all comes back to the wavelength. That core rule we just learned, it doesn't change one bit. So when a wave with a nice long wavelength hits an edge, it just kind of wraps itself around it. It bends. But a wave with a really short wavelength, it barely bends at all. It mostly keeps going in a straight line, which creates a much sharper, more defined shadow. Hmm, that should start to sound familiar when you think about light, right? All right, so we've got our main rule down. The amount a wave bends all depends on its wavelength compared to the size of the obstacle. So let's connect all this back to the real world and finally officially answer that question we started with. And here's where it all clicks. Sound waves have long wavelengths. We're talking several feet long sometimes, which is pretty similar to the size of a doorway. And that's why they bend around corners so easily. Light waves, on the other hand, their wavelengths are unbelievably tiny, so they just travel in much straighter lines past everyday objects, giving us those sharp shadows. This same idea explains why long-wave AM radio signals can actually bend over hills to reach your car, while shorter-wave FM radio needs a clearer path. And it's not just trivia. This is a huge deal in technology, defining the limits of our most powerful microscopes while also letting us map out the atomic structure of crystals. So you see, this isn't just a neat party trick that waves do. It's deeper than that. The bending of a wave around an obstacle, well, it's a fundamental property of all waves. It's just baked into the physics of how our universe works, from a little ripple in a pond all the way to the light from a distant star. Which brings us to one final thought to leave you with. We've just established that light is a wave and that all waves diffract. So why don't we see beams of light bending around us when we walk down the street? The answer is right there in the rules we just covered. Think about it.